So good morning, everyone. And for those on the East Coast, good afternoon. Um, my name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois Urbana-Champaign. And for iGuide, which is the NSF-funded Institute for Geospatial Understanding through an Integrative Discovery Environment, I play the role of the managing director. And iGuide is conducting this series, which we call VCO or Virtual Consulting Office, which we do every week, almost every week, and discussing various topics that are related with GI science and GIS broadly. And today we are very pleased to introduce kind of our speakers, Sina and Nathan, who would be talking to us about the OGC work related to a wide discrete global grid system or DGGS matter now. So this has been like standards that OGC has been working for for a long time, and now it's kind of in a state that um, it is more starting to be more widely used in the community. So highly relevant topic for this group. So I'll pass on the virtual Zoom floor to Sina and Nathan. So Sina, maybe you can take it away.
Thank you, Anand. Yes, let's start with this. Uh, my name is Sina Taghavikish. I am a project manager in Open Geospatial Consortium, OGC, and I'll present the first half of this presentation, and Nathan will present his second half, and I will let him introduce himself when the time comes. So just going through the slides here. The agenda for today is that gonna provide some introductions. So what is DGGS? Gonna talk about how to choose your DGGS in a very, very, very brief manner. When this technology became of being a technology, and why we say DGGS is important, and why is this DGGS important now? Is for that we're gonna go and delve into the pilot results, which basically a website that I'm gonna go through, and then Nathan will present the AI part of this story. So moving on to the introduction. So what is DGGS? A DGGS is a discrete global grid system. So discrete means that you basically try to make everything to a zone. So it's like the idea of the cells. So you can see the big image on the right-hand side representing basically South America. And you can see the zones identified. It's a global grid, so it means that it covers the whole planet. And it is a grid because it repeats itself, and it has a specific parameters. So it has the DGS, like a discrete global grid, is a grid basically in the same refinement level. Let's say all the pixels in all the zones that are orange. And then you have the refinement level that it has the concept of hierarchy. It's a grid and it has a concept of hierarchy. And the hierarchy means that it has parents that have children zones inside. For that, it has the relative depth concept. So it's the number of refinement levels. So it's not infinite. So it has a limitation on that part. It has the idea of subzones, means that each parent has a certain number of children that are there either fully or partially inside of it. The other concept that is important is the zone identifier. So this picture at the bottom shows that each basically zone has a unique ID, and that unique ID, as long as it does have a ZIRS, which is the zero identifier reference system, means that it's reproducible and repeatable, and that's only for that grid. That's a critical point for having a really interoperable DGGS. So the big topic that should be the focus is DGGRS, not really a DGGS. So DGGRS is R standing for reference, means that it is a DGGS. It has the ZIRS, so it has the zone identifier reference system, and it has a deterministic subzone order. So it means that you basically can identify the subzones, exactly know where they stand, how much of them are inside. So these things has to be mathematically well known. So saying that, I want to highlight that DGGS is highly mathematical concept. But the good thing about it is that the standard is out there. All the mathematics has been done. The API covers it. And now with the release of the API, which was released just in October, we do have really the basics for the programmers to use it. And we do have lots of libraries that people are providing for this. Another topics that I want to highlight regarding the DGGS is you need to know 4 topics to really understand DGGS. One is the concept of the equal area. So it means that each of those cells, imagine if they are equal area. Equal area is a big topic for the people who are in the geospatial. So I want to highlight that the most used DGGS is H3. H3 is the DGGS that Uber uses. And as you can see in this graph, H3 is horrible in the equal area property. So the best equal area properties are the ones that you can see a line here. So it's just probably this 5 at the top and a few at the bottom. So this is a topic to consider, but the H3 is used because the library support was out there. But with the new libraries out and with the new support for the other DGGRSs, it's time to move on maybe to more advanced DGGRSs as well. So another topics that you need to know are the shapes. So it could be hexagons, diamonds, triangles, or it could be mixed. So this graph, this images shows them perfectly. So they can be hexagons, they can be triangles, they can be diamonds, or they can be mix and match. So triangles, basically diamonds, or they can be completely something else, like the pentagons. That's the really they do not really not necessarily like they have a different shape, right? Let's put it that way. Another topic that you need to know is the refinement ratio. Means you can see, for example, it says IVIA 3H. So that 3 stands for 3:1, means that each hexagon, each parent has 3 children in it. So 1 children here, if you add this 3 parts, it's going to be 1 children physically and another children here. So this is a 3H. So it means that 3 hexagons can be fit inside 1 hexagon. Another topic that you need to consider is the congruency. So probably it's not the best name for it. It's the fit basically of this child zone inside the parent zone. So as you can imagine, they are imperfect. So you can see, for example, here that there are pieces from the lower triangles that are inside this and they become part of this parent zone. But that's a challenge, right? These calculations, there are calculations about it, and you have to know about it when you choose your DGGS. So this is just the main basic concepts behind a DGGS. So now I want to talk about the history of the DGGS. So it's not a new technology. It has been, the concept has been since 500 years ago. And maybe even in the contemporary context, they are DGGS implementation since 1950s. So why it is important now? So what has changed? What has changed is our computational power. And computational power is a big part of it. And another part of it is the AI. So now the DGGS can provide something that the other techniques cannot. And what else that actually matters is that the API is out. So now the implementations can be easily done. And you don't need to go through lots of mathematical concepts to use a DGGS or a DGGRS. So why DGGS? A projection problem. So the idea in the old days was we had a spherical planet. We know that. Although if you are on the flats, flat people, that's a different story. But if you're not talking about the unscientific parts. So if you do want to make a sphere into a flat surface, you will have distortions. This image is an H3 representation of the whole planet. And you can see that the pixels, that each zone has almost identical, almost equal area. Because H3 is not a fully equal area, but it is fairly equal area. So the zones in the equator are way smaller than the one in the North and the South Pole. But that's not the real case, right? The real case is that because of the distortions, we are representing the North and the South Pole bigger than what they are. But in the DGGS context, you don't have that problem. And this is possible because now we have our cell phones and computers. You don't really need a piece of paper to show a map. So another topic is that why this become a focus. So maybe one of the pioneers on really industrializing the use of the DGGS is H3, and it is the Uber. So Uber identified that if you want to find a car nearest to my place, should I go and search for all the distances for all the cars, all my Uber cars in the city? Let's assume I have 6,000 of them. That will take let's assume 14 milliseconds. Instead, I will say my house is in this grid ID, and the vicinity of me has 50 to 140 cars. So instead of looking up for the distance of 6,000, I just look for 50 calculations, and that will reduce the time drastically, right? So just give you a graph on how much, if you have a smaller neighborhood or a bigger neighborhood, the speed gonna be reduced, of course. Another part that is important in the context of DGGS is the raster vector divide. So integration is complicated between raster and vector. If you have dealt with overlaying raster vector data on the raster, you have seen this problem. DGGS will resolve this problem in future, hopefully, at some point. It does even now, but not to the extent that we do want to. But it will provide faster calculation, and that's a very big thing regarding this vector raster divide. And you can have them both in a single grid. So computationally, that's way faster than our previous methods. So now let's go to the DGGS and AI piece of the story. So why AI made the DGGS an ideal tool? So imagine you have multi-resolution analysis using DGGS zones, right? That's the hierarchy. That's just given. Then you have integration of multiple data sets. You have satellite, you have climate data, topography, social information data, population, and you have all of them in different grids. Then you have multi-resolution spatial grids that have all this data. You can move from one grid to another. Your AI doesn't need to understand, doesn't need to calculate in the backside of it the complex calculations that is regarding the coordinate reference systems. You can do data fusion, you can have federated AI models, and at the end of it, you can have AI-driven insights. So this interoperability across data sets is the big selling piece for the DGGS, or similar technologies like the TiLink, which also can you consider it as a DGGS? So it's the only way forward. Let's put it this way. If you want to really give an AI a geospatial mind, you kind of have to go with the grids. Your coordinates might not cut it. So in order to move forward, I need to talk about two other topics that we came across. So DGGS by itself is not enough for the AI to understand. So let's assume that you have the API, and the API has certain number of functions, and that's in your server stack. So you need something like the model context protocol, or what we call it, AI orchestration, to basically orchestrate your communication with the DGGS. So the nice part is that a person would ask LLM a query, like where's the flood risk? And the AI agent will use the model context protocol to interact with the server, identify what it needs, identify the functions that it needs to recall, and do all the calculations and do the repetitive process over multiple data, and at the end provides a GeoParquet or a JSON or whatever format that comes out and represent this as an outcome to the user. So a simple basically text-based query will end up with a map results. And that's a self-describing infrastructure. That's what we need. So we used MCP in this pilot. Another topic that we used was RAG, which was basically the retrieval augmented basically generation. So that is necessary because we wanted to ground our data to what it is. So how good we did it, it's a matter of question that we don't know yet. In future, we have to come up with more metrics regarding this, but we tried, right? So I want to highlight that we tried to ground to the physical concepts. So your data, your AI will know that this data that comes from this ID comes from an area, for example, of flooding that is calculated by SAR. So it can provide that information to you, and it will have an understanding of what data is if the metadata is enough. There is a transparency on this because metadata will provide you the gridding. So if there is errors in the grid, there is an inaccuracy in it, congruency problems, you will know right away. There is a semantic enrichment possibility. So imagine that you can verify the lineage of the data. You can know the provenance. So these are critical topics that needs to be highlighted. So now I want to go to the next topic. And the next one is I actually want to talk about what we really did in this pilot. So I will stop sharing my screen and share the web page. So this is a web page that our participants generated, and it is a very useful tool. If I can find it, of course, here. And I go through this because I do want to highlight the results of the pilot. It's very self-descriptive. And so let's start with some discussion regarding this web page. So first of all, I want to highlight that we had amazing sponsors, USGS, basically French Space Agency, ESA, European Space Agency, and Natural Resources Canada that supported us in this pilot. And we had amazing participants, which Nathan is one of them, which provided a feedback for us. To actually and provided us with the a possibility of doing this pilot. So the first topic that I want to discuss with you guys is imagine you are in a crisis. During a crisis, what is really interesting and what is really need is actionable intelligence. But what happens is that you have lots of data and you are buried basically under mountain of noise. And this operational experiment, this pilot that we did, we wanted to see if is it possible to cut right through that noise and get what exactly you want. So let me tell you this. In the concept of disaster management, we are basically trying to give artificial intelligence a geospatial brain. And that's the big part of what we are planning to do. And I want you to think about let's assume that what does AI can do? AI just doesn't, AI can process text, right? But only that possible to have a geo AI if it can truly understand the terrain, the infrastructure, the people, the ground, and that way goes way beyond basically just looking at the maps. You need to have AI to have a context to understand and provide truly intelligent recommendations in the crisis. And just imagine for a second that instead of having this frantically analyzing this basically data set, you just give a query in a plain English and get actionable results that you can use. And that is what's the core problem here that we try to tackle here is what we call a discovery gap. What discovery gap is basically imagine in a scenario which is in a flood scenario. Picture a flood bearing down a major city like Winnipeg. You've got satellite imagery of water. Sure, but it's in a one system. You have detailed maps of the infrastructure, power grids, completely in a different system. You have population data. Of course, it's in a third uh, system of its own. It might have its own coordinate reference system and its own structure. So all this data exists, but trying to bring it together and assembling these pieces of puzzle of this, for example, 6 data sets that we have here is uh, in these different boxes are difficult, right? And you are literally buried in the data, but starve for the actual information. You cannot get the information that you want. So now, let's say that what we do traditionally, we bring the best of our people. They spend precious hours to put this data together just to try to find the right data for the right place and stitch this data together. So the new vision that this pilot brought together was that let the AI do this. So instead of empowering the data scientist, we empower the decision makers. So the data is something that AI can understand, that can put it together and can easily understand the real world scenario. And this will actually basically try to bridge this discovery gap. And so let's talk and see what did this really work. And that goes to the like we say at the beginning of this website. I was saying that this is basically the DGGS is basically a digital fabric of this planet. So the easiest way to think about it is just consider DGGS as a universal translator that is all things location based. So it takes every kind of geospatial data that you can imagine, satellite images, flood models, infrastructure maps, and puts it in the same universal grid. And suddenly you have everything line up perfectly. You can put this together and you can come up and give this to AI and AI can actually read this. Every cell has a unique address, and that allows the AI to analyze the global data with absolute consistency. And that's what we really want, right? So did it work? Uh, Interestingly, yes. We actually brought 6 servers, so 6 different implementation of the DGGS and 4 clients together. So 4 AI analyzers, and we put them together, and we put them as 10 companies together, interoperability, and they were working together to provide one solution. So the results of this pilot actually showcase the fact that you are not vendor reliable anymore. You can actually use multiple companies and you get the same results and you can do the same analysis. And that was the biggest highlight of this report. And so I'm not going to go through the details of this webpage. I leave it to you if you are interested to go through it. And with that, I will finish my presentation and I leave the rest to Nathan.
Hello, everyone.
Yeah.
I need to send a request for permission to share,
Oh,
according to Zoom.
Yeah, I guess you have the permission, but maybe Sina, you can stop sharing.
okay. I stop sharing if that's the case. Yes.
Can you guys see my screen?
Yes.
Yep.
Well, thanks, everyone. Yeah, my name is Nathan McEachen. A little background about myself. I have a master's degree in computer science, and I have some modest publications in the fields of model-driven engineering, software testing, and actually participated in a paper of neglected tropical disease where, that involved geomatics. So I'm the founder of TerraFrame, and we participated in the OGC AI-DGGS Pilot, as Sina mentioned. And I'm here to talk about our work and then also how we're seeing DGGS fitting into an overall GeoAI strategy. And recently, we're seeing some uptake from some of, at least from one of our federal U.S. Agency customers. So the these slides are some of them have been cannibalized from a couple of presentations through the OGC, and I especially want to thank our main government sponsor, which is U.S. Army Corps of Engineers, the Civil Works Division, that is been a fantastic supporter. So, where does DGGS fit into an overall Geo AI strategy? And I think a more fundamental discussion is what is Geo AI? Is AI simply going to be something that enhances existing GIS tasks or workflows, or is it something that can enable new paradigms? And so, the objective here on the right that's depicted here is something that is a vision of the U.S. national map, intelligent national map. And that is not just to be able to give people the ability to, using natural language questions, in an ad hoc and on-demand manner, find data sets, but rather, how can the AI answer questions that involve geospatial awareness, where data between different government agencies are integrated? So if we're going to ask the question, what populated areas would be impacted by a wildfire, that is not something that a single organization has the authoritative mandate for curating that type of data, or rather that comes from the data needed to answer this question comes from different organizations, and that data needs to be integrated. And so DGGS can play a very important role in implementing this type of vision. So our work has been funded in the context of disaster response. So in addition to the AI-DGGS project, we participated in the OGC Climate and Disaster Resiliency pilots. And so our mission was to try to develop methodologies for leveraging spatial data infrastructures and taking geospatial or geoinformatics data from spatial data infrastructures and making that, or turning that into a format that could be consumable by large language models, with the objective to give users the ability to ask ad hoc and on-demand type questions that require knowledge of how these different features are related to each other, so semantic networks of features. And how do we do so in a way without using the traditional business intelligence lifecycle, which is, if I have a question, I need to find the data required to answer that question, integrate the data, and then start using my business intelligence tools. In a flood disaster response context, there just simply isn't time to do that. And it's also not, it's important not just to understand the immediately impacted area of a disaster event, like where the flooding occurred, but rather to understand the cumulative impact. What is the downstream impact of that event? And so you have disruptions to transportation. You have people who live on dry land but may not have access to healthcare because the health facility that they use has been inundated. So how do we, despite a rapidly changing picture, create this type of user experience to support decision makers? And if we can solve it for this problem, where it's very time sensitive, we basically can solve it for any number of domains. And so one of the limitations for using large language models for this type of decision support is these foundational models don't necessarily have access to local geographic contexts, specifically networks of features, so road networks, waterways. And so if you're going to ask ChatGPT if the riverbank that is close to your house were to flood, which households within your neighborhood would be impacted, it's not going to know because it just doesn't have that information. And so often RAGs are used, retrieval augmented generation is a great method for exposing additional information to the model. And so in the vector embeddings, when it comes to text, the vector embeddings group related concepts together in vector space such that they're numerically very close to each other. And that is good for grouping related context. But vector embeddings have a very significant limitation in that they cannot model networks of information. So if you want to understand which farming parcels that grow soybeans 100 miles downstream from a dam might be impacted if the dam were to breach or were to flood. You can't necessarily model that in a traditional text-based vector embedding, because that requires semantic awareness of an entire network of features, multiple degrees of separation. And so, in order to bring geospatial awareness into large language models, there are this is not inclusive, but two important approaches are: one is using spatial knowledge graphs, for which I'll get into that in a little more detail here in a bit, and that's for modeling features of networks of features according to different geospatial semantic relationships, and then exposing that to a large language model by creating a geograph RAG. But also through this pilot, we saw how DGS is incredibly useful for bringing that type of context into a large language model for aggregate and statistical data. And in all honesty, I was attending an OGC meeting in Estonia in 2024, it's Innovation Days. And in Europe, it seems like DGS has a lot more uptake than it does here. That was really the first time I was exposed to it. I saw a number of presentations on DGGS. And I'll be honest, I didn't quite understand its usefulness. But having gone through this pilot with OGC, and also showing the results to our main sponsor in this work, the value is very, very, very clear. It's incredibly useful. And so when it comes to this objective to bring geospatial data, integrated geospatial data in a more on-demand type manner, so that it can be consumed and used by large language models, you have this notion of common geography. And so the significant advantage of DGS, as Sina pointed out, is that it provides a common reference system. So if you have multiple data sources publishing their data, or it's called quantizing, so basically taking their data and converting it into the values inside these respective zones, and they're all using the same DGS, the same reference system, then these data sets come together automatically. Because when you're looking at a query from DGS backend, what you're getting is a bunch of statistical information, and within that result set, each position, you're basically getting an array, and each position or index in that array represents a location. It's an implicit identifier that is globally unique. So the idea is, if you have data being published on population, on transportation, elevation, and those are being published by different servers, you can query those servers, and all the data will come together, will be normalized by these common geographies, which are the individual zones, and also the zoom level. So, but one of the things that makes this notion of common geography not so straightforward is it's the way we manage geospatial data today. We tend to manage geospatial data using tabular data structures and not as a single source of truth. So this is a slide I have permission to share from U.S. Army Corps of Engineers, the Civil Works Division. So each row here on the left represents the same dam, the same water dam, but from a different silo. And so we as humans can look at that and infer that, yeah, these probably could be the same dam. However, if you want this to be deterministic, there's not enough certainty here for a machine to deterministically identify these as being the same structure. Well, you think, well, I'll just use the GIS coordinates. So I'll just use the geometries. Well, the problem there is that also is non-deterministic, because in the case of dam, but this is not a problem limited to dams, is you have a different representation. In some systems, it's represented as a line. Sometimes it's represented as a single point. Sometimes it's represented as a polygon. And so each silo is representing that same structure differently, geospatially, according to whatever the domain objective is of that data silo. And so if we can recognize individual features or publish individual features in a format that is like a common geography, similar to DGGS zones, then we can do a lot of great things. So the more we can automate, the more we can use large language models. And also a lot of what I'm saying here pertains to geospatial foundation models as well. So these zones are, you can take statistical and aggregate data that is quantized by zones, and according to those zone IDs, you can actually embed those in a vector space to do some predictive analytics. But our work is primarily focused on using large language models. So once you get a DGS layer or a result set from a query, then you can determine, well, which features are overlap with those respective zones. So the idea is that if this represented flood data, you could then find out what communities might be impacted. And so when we demonstrated the results of this pilot to our customer, one area where they immediately saw value is that when it comes to modeling inundation data, so the U.S. Army Corps of Engineers has run a number of flood inundation scenarios. So let's say you have a given reservoir, and what if it floods by a certain amount? So they have, and then what if it floods even more? So they have already done all these calculations to determine which areas would be impacting according to how severe the flood is. And they're currently modeling that information or storing the information as polygons, which that makes sense. And so from an analytics standpoint, it's a really great, polygon is the perfect representation of that. However, from a decision-making standpoint, how do we make that data, how do we organize that data in a way to where it's findable and it's queryable and consumable to support operational decisions? It's actually quite a mess, because for the same inundation scenario, you have, we've seen half a dozen different polygons. And so by quantizing that information in using DGGS, you can then publish those different scenarios, those inundation scenarios, as different in such a way that you just have a single interface for clients who want to consume that information. It's a much more standardized sort of API abstraction for getting that statistical data, and then also specifying what zone level, what level of granularity do you need that information. So their Army Corps is looking to implement that potentially this year, which is exciting. So in order to understand, before I dive into my demo here, I want to give dive a little deeper into spatial knowledge graphs. So unlike feature classes, which are feature-centric, a spatial knowledge graph is a data structure that is feature-centric. So if you were to ask a waterway segments table, what administrative boundaries do you flow through, that table is not going to have that answer. Someone has to actually probably do geometry arithmetic and integrate it with the administrative boundaries table to come up with an answer. But it's not formally, there's no abstraction that can formally manage that. So once you've done that integration, that's typically not something that you can publish as a first order object that can be discovered by the broader community. Well, so spatial knowledge graphs represent features as nodes in the graph. And the idea is that you want to have one node, back to this notion of common geography, just as you have standardization on zone IDs, depending on the reference system. You want to have one standardization for each geography. So one representation in the graph, one node, and then the edges in the graph have a semantic label according to the geospatial, their geospatial properties. And so then when you're building a knowledge graph, you translate your integrations from your feature classes and model those properties as edges. And because you have a semantic label attached to that edge, that is what allows the model to then bridge the gap between your natural language query and then actually querying the graph database. So it converts your language into a graph query. We've done Cypher, but right now we're using Geosparkle. And the advantage of that approach, along with DGS, is that the results you're getting from the model are traceable to its source. Hallucinations are manifested in terms of, for like a faulty generated DGGS API call or a faulty Geosparkle query. And potentially you could have it generate legitimate code, but maybe the model is answering a slightly different question that you asked. But regardless, you have that full traceability. And so you can, through agentic orchestration, you can then you can then create an experience where when you're asking a question, it knows which tool, that's where the MCP comes in that Sina was mentioning, which tool it should use to respond to the user's question. So if I ask a question that really is in the realm of DGGS, then through configuring the agent, it then knows to call a DGS backend. If I'm asking a question that involves understanding networks of features, it then calls a spatial knowledge graph. And so the workflow is, and something also we discovered is one of the strengths and weaknesses of DGGS is what you're getting back is, like I said, is an array. When you make a call, you're getting an array of those values. And the index in the array represents the actual zone. It's implicit the zone ID, and you're not actually passing in any geometries for the actual rendering of the shapes or the hexagons if the reference system is actually little hexagons. That's rendered on the server. It's just these are common geographies. So the downside of that is when it comes to interpreting them from a model is text-based, and a model doesn't necessarily understand an array filled with statistical values. And so what we're using is spatial knowledge graph to help identify the AOI or the area of interest. So basically centering the question around an area that the human can express using natural language, and then based on that context, then translating that into a corresponding DGS API call, also using something called CQL2 so you can actually query some specify more specific queries such as a flood level, which I'll demonstrate here in a bit. And so by orchestrating the agent knows that first we got to understand the area of interest. We then query the DGS server that has the desired information. Then client side, we then detect the overlap between what we call geo objects or the nodes in the graph. And then from there, we can generate a Geospark query to understand that downstream impact. And so this is the objective for Army Corps Civil Works, is that they will be able to publish publish data in terms of DGGS and also spatial knowledge graphs themselves using open source software. So with that, given the time, I think I might have gone a little over. Let me dive into the demo. Can everyone see my screen?
Yes.
Okay. So what we're looking at here is an application that we're calling the Geo AI Kaleidoscope. It is an open source reference implementation for how you can build these types of interfaces where you can ask natural language question, you can get a result back, and then you can display that result on the map. And then in some cases, trace into the answer by looking at, let's say, the spatial knowledge graph. So I just asked it, what kind of data sets can this solution provide? And so through configuring the agent, we've told it about the different backends that are available, and those backends come from different participants in this OGC AI pilot. So now I'm asking what data. I just repeated that question. I apologize. Now I'm interested in flood data because Natural Resources Canada was one of the key sponsors of this project. And you'll see the map is centered around Winnipeg. So so when it pertains to flooding, it lists what's available for me to query. So now I'm going to ask a more specific question. Show me the data for flood level in Winnipeg where the water course is false. Water course meaning where the water is not supposed to normally flow. And so what I just, in the interest of time, you saw me click through right there is there was some ambiguity in my question. It says, well, there we have two Winnipegs. We have Winnipeg on the coast, and then there's the city of Winnipeg. So I was given a list of options for disambiguation. And so then here we have the information broken down by the individual DGS zones. And so now that I know where there is flood risk, I want to see what the cumulative impact is. And so I'm going to ask for impacted roads. Yeah, so what it's doing now is it's translating my natural language question into a database query. So then we see impacted roads. And then I want to leave enough time for Q&A, but also, we modeled some population data relative to power infrastructure to show how this solution could, given that on-demand query for flood level, what power infrastructure would be impacted, and then from that, which populated areas would then potentially have a loss of access to power. And what that shows is people definitely can be affected from a flooding event who are not necessarily within the immediately impacted area. So that shows that this is a great approach for modeling and discovering those downstream unintended or perhaps unforeseen side effects of the immediately impacted area. So I will stop here and leave it open for questions.
Thank you so much, Sina and Nathan. That was really great presentation. So let's open up the floor for questions. You can feel free to unmute yourself and ask questions or type it on chat, whichever is most convenient for you.
And when I'm sharing my screen, I can't see not seeing the chat. I'll go ahead and stop sharing.
If there is one, I'll let you know as well. Any questions for Sina and Nathan?
Hi, I was wondering how long it took you to set this up. Is this something that's doable for, say, university groups to do, or do you think that this is something more intense? It really takes a lot of partnerships between state, federal, and organizations such as yourself to put these pieces together in such a way that it is usable for the general research community.
So I'll take the first stab at the answer. So this pilot from scratch to the end started in, I believe it was in August, Nathan, if I'm correct, or was in, I think
July.
It was July. So in a matter of basically 6, 7 months, we set up everything from scratch. Like we put the DGGSs together, we put the AI pieces together, and there was nothing before it, except that the libraries for the DGGS existed to a certain extent. But needless to say, the people who were actually providing the DGGS libraries were actually involved in the event, right? And since the start of it in 6 months ago to now, it has been dramatically changed. Like the libraries are super easy to use now. They have guidelines to use now. If you go to the web page that AI-DGGS Pilot, which Anand kindly shared, if you go to the pieces that is the servers, you can find basically 6 different implementation. They're all open source. You can all download those libraries, use them as much as you want. Very easy to use. One of them is Safe Software. Want to highlight that. It's actually an industrial solution. So if you are familiar with Safe Software, with their famous app FME, which is very widely used in the geospatial community for converting the data types together. So they even have a DGGS, and we're hoping that this will be soon supported by Esri and the folks like that as well, because there is no other way around it. And if FME supports it, it's way easier for Esri to support it. So in terms of implementation, it is very easy to implement because the libraries are there. It's just a Python library. Regarding the AI piece, I leave it to Nathan because he's the expert.
Yeah. Yeah. So so we participated on the client side. So we weren't publishing data using DGGS. But if once the data sets are published, it's actually not that difficult to configure an agent to create an interface for users to actually query the backend. Where it gets a little, it requires more effort is actually building that user interface, so that that user experience I showed. We're showing it on the map and interfacing with the chatbot interface. That could take a little bit more time, but like our reference implementation is open source. And so I think the idea is that either our tool or other tools will reach a state where it will be pretty easy and straightforward, where all you have to do is just you can use the tool as is, but you just need to just configure the agent to let it know what type of data are we dealing with and where do those different data sources reside. And so I want to share with you guys, for those who are interested in getting your hands dirty, can you guys see my slides again? Yes, it looks like you can. So if you look at that link, go ahead and take a screenshot. That is a link to a workshop that I gave at FOSS4G North America last November. Now, it doesn't involve DGGS. It's just spatial knowledge graphs. But we've been requested to see, could we update this hands-on workshop to include DGGS as well for potentially for an upcoming conference. But regardless, in this state, you can see what it takes to configure an agent in order to generate GeoSparkle query for data that's a spatial knowledge graph, and also how to build the spatial knowledge graph. So if you just are curious to see what does it look like to configure an agent, you feel free to look there. And like I said, hopefully we'll within the next few months potentially have this updated to include an example for DGGS as well.
Okay. I see 2 questions online. Andy asks that there must be a standard projection, scale, and registration for the hexagons at different levels to flow data together. How is this usually chosen? For example, with the state plane projection. So first of all, DGGS is just a resampling of the data set, right? So if your data set has a certain projection, it's WGS84, it is in UTM, it's 3TM, it basically follows the same thing, right? But the whole trick and the whole point of DGGS is that this is done once normally when the data provider provides this data, and then the users will bear the burden of the conversion, right? But instead of imagine that you do this conversion each time, you do it once, and that's basically the additional basically use of DGGS. And the different levels, it's a mathematical resampling. So if you basically calculate in one zone level, which is at a lower level, then it's very easy to do the rest of the zones. And the library itself, basically the libraries itself, for example, the one that provided by Ichere, the DGGAL, will automatically do that most of this for you in the backend without you need to thinking about it. So Ichere is one of the participants in the pilot, and DGGAL is one of the main libraries that everybody used in this pilot. And I hope this answers your question. Not sure if I'm hearing.
Yes, that's very interesting. I need to look into it more to see how it all works.
Yeah, the issue with our US partners is that this is happening a lot in Europe, and it's followed up in Canada as well. But we're not seeing that much use of it in US, although it's not true. Like you can say Google S2 is actually DGGS, and there are databases that already USGS provides that are somehow kind of DGGS. The whole point of it that we want is the interoperability. As long as they follow the standards, then they're interoperable. Then the libraries can convert from one to another. And it's not that hard. It's just the computationally challenging for some of them. For some of them, not. If they are following the same basically structure, let's assume that, for example, they're covering the same idea of hexagons and the same the ratio, refinement level ratios. That's very fast and easy. If they're not, then you have a conversion step in between. So I just wanted to highlight that. I see another question by Zhu Shi. I'm hoping I'm not pronouncing it wrong. Although I have not previously worked with DGGS, I'm concerned about the presence of 20 pentagonal cells within an otherwise hexagonal tessellation. These irregular cells may affect the neighborhood structure and distance calculations, potentially introducing uncertainty in the proximity analysis. Have others encountered this issue, and how is it usually handled in practical applications? This is a great question, has a great amount of discussions in the pilot. That's the congruency issue that I highlighted in the presentation. Right now, the library handles it, and there is a lot of mathematical things that happened throughout the pilot to address so many of this, specifically regarding H3, is that the tiling that H3 has is not necessarily OGC compliant. The libraries are not, but if you can make it compliant, and this matter of this error calculations, it is actually covered in the engineering report. The engineering report has not been released yet. That's the documentation that OGC provides. That's open to the public. And whenever it will be released, I will share it with Anand and with iGuide so the public can use it. And this discussion has been in detail covered there. And we are also planning to make the GitLab public, which has this discussion as well. And yes, this is an ongoing discussion, but it's not a problem. It's a mathematical uncertainty, right? So as long as you know, you can choose grids that do not have that at all, right? You can have grids that have absolutely no, like the least amount of issue with that. Not too sure if it answers your question.
Thank you. I think thanks to both Sina and Nathan. Maybe one last question if there is one, but I think we are running out of time, so we'll try to wrap up very quickly. Okay. Again, thank you, everyone.
There is a question, Anand.
Yeah, go ahead then.
Ahmed is asking, I know you touched a bit on that, but I was wondering if you can highlight the advantages of SKG versus the DGGS tackling the same downstream task, especially for implementation, deployment, and overall performance. That's, Nathan, a question for you. You're mute.
Thank you. Sorry about that. Yeah, so the DGS, great format for representing statistical and aggregate data by your region. And so the spatial knowledge graph excels something different, and that is modeling networks of features. So when it comes to understanding a particular area of interest, let's say flood risk area, that would be for DGGS. So once that area is highlighted, then you want to understand, okay, well, what is the cumulative impact of this particular event? That's where the knowledge graph comes in. In the knowledge graph, you can build transportation networks. You can build hydrographic models. So they're incredibly complementary. I mean, they overlap very little as far as what they're intended to do. And so, let's see, the rest of your question is deployment and overall performance. There's a lot in that question, so I'm trying to think of how I could answer it. But for understanding those relationships, several degrees of indirection, a spatial knowledge graph is far more performant than, say, spatial data tables or a racial database.
Yeah, I want to highlight that again. I think they are complementary. Like, kind of, if there are technologies that have to be used together, if you want to put it the best way.
Thank you. I think thank you both, Nathan and Sina. Really appreciate you. I think this was a very interesting topic, and I guess that's reflected by the questions also. And there is a lot of interest in the community. So thank you so much for doing this. I'm sure you'll come back at some time later this year and give us some more updates, and we can schedule that as well. But as I said, this VCO series happens regularly. We have at least 2 of the next upcoming VCOs here. You can sign up for our mailing list and get notified of all our VCOs, or you can go to our website, i-guide.io, i-guide.io, and then click on the VCOs and to find all the VCOs. The video recording for this VCO will also be available online by the end of this week. And we would look forward to seeing you at other VCOs in the future, which are on related topics as well on AI. Thank you so much again to both Sina and Nathan for doing this for us, and thank you for others for attending.